Welcome everyone to part 3 of the chapter 9 lectures. And so what we've been covering is the circulatory responses to exercise for this chapter. In the first two parts we discussed the anatomy and physiology of the heart. And in the second part we discussed the electrical activity of the heart and the blood flow through the heart and how it's oxygenated. Now we're going to actually start moving into the responses to exercise. More importantly, we're going to discuss in this particular video the cardiac responses to exercise. But first, before we get into that, let's get into the why or the purpose of this. And why is it important to understand how the heart reacts to exercise? Well, really what it comes down to is the main portion of this entire class. And if you go back to when we start discussing with this class and all the components, what do we need for exercise? Right? We need energy. And what energy do we need? ATP, right? And so understanding how the heart reacts to exercise all comes down to ATP synthesis. Because the blood is the pump that provides oxygen to the working muscle. And this component is necessary to produce ATP. And this is why it's important to understand how the heart reacts during exercise. Also, let's do a quick review on the nervous system. And so in the past, particularly in Chapter 7, we discussed with the nervous system that it is broken down into two components. You have the central nervous system and you have the peripheral nervous system, right? And the central nervous system has three components, again, which is the brain stem, and the spinal cord. And the peripheral nervous system is broken down into two components. You have the somatic nervous system and the autonomic nervous system. Now, of course, the autonomic nervous system has the parasympathetic nervous system and the sympathetic nervous system. Here we talked with the somatic nervous system in Chapter 8 with skeletal muscle, right? Now, we're going to be focusing more on, clear this out, the autonomic nervous system, right here. This is going to be our focus over the next few slides, particularly the parasympathetic and the sympathetic nervous systems and how they affect the heart. Additionally, let's talk about the neurotransmitters for the parasympathetic in the sympathetic nervous systems, right? So we talked about we mentioned this in chapter 7, the different neurotransmitters that accompany these two portions of the peripheral nervous system. The parasympathetic nervous system has only acetylcholine as its neurotransmitter, okay? Now, with the sympathetic nervous system, you have three different neurotransmitters. You have norepinephrine, acetylcholine, and epinephrine. Now, epi is primarily produced by the adrenal glands, so let's just forget about this for right now. For the rest of this lecture, we're going to be primarily focusing on norepinephrine for the sympathetic nervous system and acetylcholine for the parasympathetic nervous system. And looking on how the autonomic nervous system controls the heart, let's do a quick review of the key electrical components of the heart. So here we have the SA node, and here we have the AV node. And of course, here we have our bundle branches and our Purkinje fibers. This is all stuff we discussed in the last lecture. Go and clear those out. And so what happens is communication of the autonomic nervous system starts here in what we call the command center here in the hypothalamus. And these signals are transmitted down through the brainstem, down through the spinal column to the different components of the autonomic nervous system, again, which is the parasympathetic and the sympathetic nervous system. For the heart, the parasympathetic nervous system transmits the signals to the SA node and the AV node via the vagus nerve. Now, for the sympathetic nervous system, those signals are transmitted to the different components of the heart. Again, for the sympathetic nervous system, where it connects to the SA node, the AV node, also to the bundle branch, and the Purkinje fibers. And again, this is our sympathetic nervous system nerve. And so, kind of reaching back to what we mentioned in the previous slide, let's go ahead and clean this out. And so, with this, the parasympathetic nervous system, when it communicates with the SA and AV nodes, its neurotransmitter is acetylcholine. And with our sympathetic nervous system, when that communicates with the SA-AV node, the bundle branch, and the Purkinje fibers, the neurotransmitter, let's go ahead and fix the ink here real quick. The neurotransmitter is norepinephrine. And why this is important? Because when we look at the parasympathetic nervous system, we know that kind of reduces activity, whereas with the SNS, it causes an increase in activity. The other aspect with this too is look how the PNS and the SNS nerves innervate the heart. You know, the PNS only innervates the heart and really regulates it at the site of the AV node and the SA node, right? But here, look at let's clean this out real quick. You know, look at the site of where the SNS innervates and controls. It's 2 sites compared to 4, right? And this is important because of the functionality of the heart and how it's getting the oxygenated blood to the body as quickly as possible during exercise. And so let's move on into that portion of the lecture. There's a couple of key elements that we need to discuss when we're looking at the characteristics of the heart and how it affects getting oxygenated blood to the body during exercise to create ATP. The first is what we call is stroke volume, or SV for short. So stroke volume is the amount of blood that the left ventricle can push out into the system. During one heartbeat. Okay. And this is dependent on the size of the chamber or the size of the left ventricle and the strength of the contraction of the heart. The second component we want to discuss is the characteristic called end-systolic volume, or EDV for short. And so all EDV is the amount of blood returned to the heart by the veins. That's all end-systolic volume is. End-systolic volume is really dependent on a couple of different characteristics. And so, for example, one of those is blood pressure, right? The overall systematic blood pressure of the system. Two is what we call the muscle pump. And all the muscle pump is the muscle's ability when it contracts to help venous return during movement. And three is, depending on heart rate too. So basically stroke volume and EDV, they are highly interdependent. And we say that because there's a mechanism called the Frank-Starling mechanism. And basically all this says is when you have an increase in end-systolic volume, this will cause an increased stretch of the heart muscle. And so, in turn, what this does is give increased contractility of the heart. And finally, what that means is there's an increase in stroke volume. So, bottom line is to really kind of summarize this up, clean this out, that the Frank-Starling mechanism essentially states in very short terms an increase in end-systolic volume equals an increase in stroke volume. Okay? And so when you have an increase in stroke volume, that means you have an increased blood output by the left ventricle of the heart with each heartbeat. Now, these components are important because what this does is it allows us to kind of quantify the amount of blood that the heart is able to output per each beat. Now, there's another important concept that I want to bring forward is what's called cardiac output. You also sometimes see this as Q. And so what cardiac output is the amount of blood. Clear that out. Let's try this again. Cardiac output is the amount of blood that the heart can pump in 1 minute. Okay? And this is more of a metric that we tend to use in the field more than stroke volume. And so the mathematical equation for cardiac output is as follows. It's heart rate times stroke volume. Okay? And so heart rate is beats per minute. And stroke volume is in milliliters. Okay? So basically, at the end of the day, when we look at our units, our cardiac output is liters per minute. Okay. That's the end units. Now I say this and I show you this equation because it gives us the ability to kind of look at the factors that affect cardiac output. And so again, Q equals heart rate times stroke volume. And the heart rate is dependent on PNS activity and sympathetic nervous activity, right? Also, sympathetic nervous activity does affect stroke volume because it can also increase contractility, is similar to what we talked about, the Frank-Starling mechanism. Also, stroke volume is affected by, again, contractile strength. Basically, how hard is the heart pumping per each beat, right? It's not just the rate, but also how hard it pumps. And also, stroke volume is affected by end systolic volume, which is what we discussed. And so when we have increases in, say, SNS activity, you have increases in strength of the contraction, which then eventually cause an increase in end systolic volume. These will affect how much stroke volume or how much blood is pumped out, which means we have an increase in the stroke volume. Furthermore, we can keep stroke volume the same, right? But if we have if we have an increase in the heart rate, right, that means we're still going to have an increase in Q. So with exercise, we know we have increases in heart rate. We detected that during the blood pressure lab, and also conversely, you will have increases in stroke volume as well. So with an increase in either one of these variables, you will have an increase in Q. And so why do I go over all of this? Well, because these are the ways that we can quantify how blood is pumped throughout the body during exercise. And again, our primary marker of this is going to be Q. All right. So we can measure Q during exercise. And so with this measurement, if we see increases in Q during exercise, we can essentially measure how much blood is going to the working muscle. And so you need to keep this this variable in mind because we'll discuss this relationship on how workloads come chapter 13. So let's recap. We covered quite a bit during this lecture. So let's do a quick summary. Let's tie it down to just a couple of key components that you need to take home. So first, again, we covered the nervous system on how it affects the heart, right? And here we discussed how where the PNS innervates the heart at the AV and SA nodes. Whereas the SNS system, right, innervates both at the AV, SA nodes, the bundle branch, which I'm just going to call BB, and the Purkinje fibers. And the reason for the SNS having greater innervation is because we know that the sympathetic nervous system causes increases in heart rate, right? And so it needs to be able to, and it does that through affecting the AV and SA nodes. It also increases contractility of the heart. And it does that where it innervates both the bundle branch and the Purkinje fibers. That's the first portion here. Let's clean this up. The second, we discussed a couple of different variables of the heart. The first is stroke volume, or SV. And again, stroke volume is the amount of blood pushed out by the left ventricle in one heartbeat. The second component of this we discussed is end-systolic volume, which is the amount of blood that's returned to the heart via the venous system, or the veins of the circulatory system. Now, these two are highly interrelated, right? And what we said, through the Frank-Starling mechanism, is an increase in EDV will cause an increase in stroke volume. And this is due to increased contractility of the heart. And lastly, the third was cardiac output, or Q, which is basically heart rate times stroke volume. And Q is basically the amount of blood that the heart can pump in 1 minute. So if we have an increase in heart rate or an increase in stroke volume, means we'll have an increase in Q, which means more blood to the body. And bottom line, what happens if we have more oxygenated blood pushed to the body? That means we have the potential for increased ATP production during exercise. That's why this is all important. Thanks for your time, and I'll see you in the next video. Take care.